All right, well, I want to thank Avi and Hussein for inviting me here to this workshop. And of course, I want to thank everyone for staying around to the very last talk of the last day, late in the evening. And so I'm going to go back to much higher redshift than what we've heard today and talk about chemistry in the early universe, building on some of what Daniel Savin told us earlier today, where Dan gave us the experimental perspective. I'll talk about the theoretical atomic molecular perspective. Let's see. If this works. Okay, too far. Okay. So what I'm going to discuss is basically one topic. But first I'll give you just a little overview of primordial chemistry, and then I'll discuss issues related to photodestruction processes, how they are included in chemical networks, and then look at the main topic of distortion photons on photodissociation processes, which is motivated by the beautiful recombination spectra produced by Jens and others. And then finally, I'll look at the H2 plus channel for making H2, the kind of often neglected pathway to make H2 in the early universe. Okay, so let's see. So just to make sure everybody's still awake, hope everyone's had their dose of caffeine, you may look carefully at this picture. Right, we have a USB plug in there. So that's the next thing for Steve Jobs to work on. Okay. Okay. So a brief overview of hydrogen chemistry. So this is the chemistry where we have a lack of dust particles, right? So the formation of molecular hydrogen is purely through the gas phase. Okay. Do we have a pointer? Right there. Okay. Okay. So, so the chemistry, which was kind of proposed back in 1962 by McDowell, is first you begin with hydrogen. After hydrogen recombination, we have neutral hydrogen combines with the electrons through a process called radiative attachment, making H-. And it turns out that Alex and Kingston made the really first accurate calculation of this rate coefficient about in 1963. And once you make H-, okay, then you can make H2 by associative attachment. That's the process that Daniel discussed earlier today, which they have the most recent measurements and calculations for this process. Okay, so that's the dominant way to make H2. This process is suppressed by ways to destroy H-. So for example, photodetachment, okay, where H- in a photon detaches the electron. And many calculations have been done for this process, and typically what's used in astrophysics is cross-sections by Wishart. And another process, which Daniel also discussed, is mutual neutralization, where we have a proton and H- collide and remove H-. Okay. So those are the basic reactions that you need, and this is presumed to be the dominant way to make H2 in the early universe. Okay. And then you could put those in a bunch of other reactions into a basic reaction network, and you can get out the abundances. So I'm plotting here the fractional abundance with respect to hydrogen as a function of redshift. Okay. And here's just a typical example. So there's protons, there's neutral hydrogen, okay. And then H- down here, and then this is the H2 abundance. Okay. And we could discuss all those little features, what they mean, but most important thing to notice is we generally don't make more than about 10 to the minus 6 abundance of H2 in the recombination era. Okay. And a number of people have done these kind of calculations. Okay. So, well, let's go back one second. So you may notice the important thing here is H-, its abundance rises really quickly here because of the efficiency of photodetachment declines rapidly as the universe expands. Okay. And so what's important in the early universe chemistry is understanding photo processes. Up too fast. There we go. One more back. Okay. And in most astrochemical networks, early universe or for interstellar clouds, etc., one of the most uncertain kind of reactions that enter the network are photo processes. Okay, it's generally pretty straightforward to calculate the cross sections, standard quantum mechanical techniques. But the main issue is the photo rate depends on the radiation field, right? And of course, the radiation field depends on what is the source of the radiation, and also what are all the absorbers inside the gas that you're studying. It could be atoms, molecules, dust. Okay? So the photo rate is very sensitive to the environment. Right? So you really need a local photo rate to actually do the chemistry accurately. Okay. So you usually don't know all those things when you start your model. Okay. However, of course, an astrochemist would like to have some pre-computed rate to use. Okay? And they do that. Okay. Okay. Well, for the early universe, it's relatively simple because, of course, we don't have dust. And the radiation field is fairly simple, right? It's almost a perfect black body. So we could easily get all the photo rates pre-calculated. Okay. And so most early universe models use photo rates based on black bodies. Okay. Or even more simpler, we could use detailed balance. I can discuss later. Okay. Okay. Well, so the subject of this meeting, of course, is more than just the CMB. There's also the recombination spectrum. Okay. Okay. And you look over here. Here's a calculation by Wong, Seeger, and Scott, earlier one. So here's the CMB spectrum as observed today, and then hydrogen, helium, and helium plus recombination, okay, are shown here, and you get this flux sticking out here from the Wien tail of the black body curve. It looks pretty small, right? It's how many orders of magnitude? 8 orders of magnitude from the peak. Okay, but it was pointed out here 6 years ago by Schweitzer and Arata that these photons could actually be very important in ionizing certain species. And for example, in this paper, they looked at lithium ionization. Okay. Okay. So therefore, the process could also, these photons, distortion photons, could also influence other reactions in the network, such as, for example, H-. Right? So typical networks include photodetachment, in which we only consider the black body radiation field. So today I'm going to add distortion photons also to see what effect they have. Okay. So here's a typical cross section this is for H- photodetachment. So photon energy versus the cross section. It has a threshold at 0.75 eV and peaks at about 1.5 eV. And this is just a fit to the calculations of Wishart, which is commonly used in astrophysics. Okay, so I can take that cross section. Oh yeah, I'm not going to show you any equations, and not going to go through all the gory details of the calculations, but just going to show you results. So with this cross section and the black body radiation field, we can calculate the photo rate. Okay. Okay. So here's the photo rate. Okay, for photodetachment of H- as a function of the radiation temperature, the temperature of the black body. Okay. And so the blue curve is the black body rate. Okay. You can see it falls off very rapidly. This is many orders of magnitude. Okay. And then if I take the distortion spectrum from that Wong et al., just using the Lyman alpha part, okay, we calculate this rate due to distortion photons, right? So really, when I put this on this plot, I had to convert the redshift to the radiation temperature. But effectively, this is a plot versus redshift, okay, of the rate, right? So over here, see, it's negligible compared to the black body. But as the black body rate falls for H-, the distortion rate becomes relatively large. Okay, right? So I can add this to a chemical network and see what contribution it makes. Okay, so here's a fraction, just plotting now the H- abundance, fractional abundance versus redshift. The blue curve is if we just include the black body rate, and then the red curve I add in the distortion photon rate. So the rise in the H- abundance is due to the fact that the black body rate is decreasing rapidly. But if you include the distortion photons, you can see that it cuts off this little peak here. Okay, so reducing H-. Okay. This fall in H- over here is due to the fact that H- is then getting used to make H2. Right, so that's the destruction makes H- over here at these smaller redshifts. Okay, well, so that's interesting, but what does it do to H2? Right, so here's a plot of the H2 abundance, okay, fractional abundance versus redshift again. And I just zoomed in on the later redshifts. Okay, so the blue curve again, if we just have H- black body detachment, okay, and we go to abundances about 10⁻⁶. If we add in the distortion photons, we can see that we drop by more than a factor of 2. And this was pointed out in a paper in 06 by Harada and Pradman. Okay, I'm sure I got that wrong. Okay, and so they did a similar calculation and showed this. Okay, well, we can go on and see what else this implies. Oh, before I do that, so this, I mentioned the blue curve was calculated by Wishart, but since then, and even before then, there were many more advanced calculations of the photon attachment cross-section. And if you push the atomic theory, including, say, R-matrix types approaches, you can do a much better job than was done in 79. And even if you go to higher energies, you get auto-detaching resonances and other effects that appear. Brendan McLaughlin and Hussein had worked on this. And we pointed out that this featured 11 EV, which is an auto-detaching resonance, could have some important implications, for example, for clouds outside of, for example, these 10 to the 5K population 3 stars, where you could have very high intensity of radiation at these energies. But it's not important at all for the distortion photons. Okay. Let's see. But anyway, I actually use the red curve to calculate those rates that I showed previously. Okay, so let's go a little bit further into the chemistry. Deuterium chemistry is also of interest. Okay, and you first might think, okay, well, just replace H by D, and we have our deuterium chemistry. Okay, so we can have radiative attachment, same as radiative attachment, D plus electrons that makes D minus, and then associative attachment. And you have two channels, H plus D minus or D plus H minus make HD. Okay, well, we saw Daniel's talk earlier. Find out that actually these are not the important ways to make HD. In fact, the dominant way to make HD is through this ion exchange channel. So D plus with H2 makes HD. That turns out to be far more important. But anyway, the D minus could also be removed by photon attachment. And also this channel is suppressed by this charge exchange reaction D plus plus H, which removes some of the D plus. Okay. So let's see what the distortion photons do in the deuterium chemistry network, okay, with that being the dominant way to make HD. Okay, so again, plot of fractional abundance versus redshift. Okay, this is the HD abundance. The blue curve, if we only have H minus black body detachment. Okay, so by the way, so let's go back. So this reaction suggests that HD should just track H2. Okay, whatever we have for H2, we should have the same kind of behavior for HD. Okay. And basically we see that same behavior. Okay. And if we include the H minus distortion photons, or distortion photons on the H minus rate, we again get another factor 2 drop now in the HD abundance. And just to check to make sure that the other channels are not too important, I put in D minus. Okay, so I use the distortion photons to get the D minus detachment rate. And you can see a little green curve. It's just slightly smaller. So yeah, that's not a very important channel to make HD. Okay, let's see. Okay. So let's look at another case. So we also have helium, right, being recombined. And we can look at the helium chemistry. Helium chemistry is a little bit different because helium minus doesn't exist. Okay, so we don't make helium through that channel. So only we make helium molecules is we make helium molecules through radiative association processes, such as helium plus with H, make HH plus. Okay. And it's destroyed by the reverse process, photon dissociation. Okay. Or we could have helium with protons, also make helium H plus, and helium H plus is also destroyed by the reverse of that process, another photon dissociation process. Okay, so those are the way to make and destroy helium H plus. And what's interesting about it is also that this reaction, helium H plus with H, goes on to make H2 plus, which turns out to be an important destruction mechanism for helium H plus. Okay, let's see. So we calculate the black body rates for these photon dissociation rates, and also see how do the distortion photons affect the helium chemistry. Okay, so just a word about molecules. Okay, so molecules are more complicated than atoms and ions, right? And what we would really like to do is to, okay, so here's a molecular potential curve. This actually turns out to be H2 plus, right? And there are a whole mess of rotational vibrational levels. So we like to know the population of each of those levels and multiply the level by population by the cross section, and then get some total rate. Okay, well then we need to know what those populations are. Well, for most ions, turns out it's not very easy because most of the collision rates are not known. For neutral molecules, they are, but molecular ions, they're not known. So it's difficult to estimate the populations. Okay, so what we can do is instead assume a Boltzmann distribution for those populations. It may be okay. So that's what we did. Right, so we calculated the cross sections from each rotational operational level, and then multiplied by Boltzmann population to get the total dissociation rate. For example, for this reaction. Okay. And first I'm going to show you, we're going to consider just photodissociation within the ground electronic state, or a so-called row vibrational dissociation. Okay, and so here's a plot of cross sections that we made for helium H+, so cross section versus wavelength over a large range of wavelengths. Okay, for various temperatures of the gas, so this is the LTE rate, or cross section. Okay, so this is 500 Kelvin, 1,000 Kelvin going on up. Okay, so within that cross section, we could then calculate the photodissociation rates, okay, which are shown here. Okay, so for HH plus photodissociation, again, photo rate versus temperature. Okay, and the blue curve is for the black body rate. But instead of using those cross sections, instead of what we did was to use the rate of association rate, okay, and multiply it by the equilibrium constant for dissociating HH plus. Right? So you just need to know the equilibrium constant. A common thing that's done in planetary or stellar atmosphere modeling. Okay. On the right direction, this way. Okay. So that's the blue curve doing that. And now the green curve actually calculated the black body rate using those LTE photodissociation cross sections directly. And you see it looks that the detailed balance approach works pretty well when the rate is very large. But this starts to depart a little bit down here. Okay. And then also using our LTE cross sections, that I calculated the distortion rate, or the rate due to distortion photons, shown there in red. Okay. And then again, put that into our early universe chemistry model and see what the effect is. And, well, turns out to have no effect whatsoever. And I can show you why in a minute. So I plot here in green the HH plus fractional abundance. Okay. And so distortion photons don't add any to the dissociation of HH plus. And here's the reason. Okay. Probably didn't look at the scale before, but here are the cross sections for HH plus, okay, compared to the H minus cross section. Okay. And the most important cross section is this one. It's in red. 500 Kelvin, okay, 8 orders of magnitude difference. Okay, so I could have guessed before doing the calculation it was going to be important. Okay. Well, I could say, well, there must be other ways to photodissociate HEH plus. Okay, and so instead of going through row vibrational channels, instead through an electronic channel. And yes, there are, and we computed the cross sections through the electronic channels, okay, and that's given here by this blue curve. Okay, so the red curve is the row vibrational channels that I showed earlier. That's just called the X to X transitions. And this is the X to the first excited state, the A state. Okay. And yes, the cross-section is many orders of magnitude larger. The problem is that it has a threshold which is even shorter of Lyman alpha. Okay, so distortion photons will never even reach those cross-sections. Right? So HH plus is not going to be dissociated by distortion photons. Okay. Okay. And even I didn't include this even in the black body rates because you can see I plotted here black body cross section rate. Black body distributions. Okay. And you can see you have to even get up to 10,000 Kelvin before there's any significant contribution from the X to A transition. Right. And at that temperature corresponding to those redshifts, HH abundance is already very small. Okay. All right, so let's consider one more molecular ion, that is H2 plus. Okay, so another way to make H2 is through this mechanism, where we first start with H and a proton, and they radiative associate to make H2 plus. And then the H2 plus collides with hydrogen to charge exchange to make H2. This is called the H2 plus mechanism or channel. Okay. And this mechanism, this channel is suppressed by two processes, just direct photon association of H2 plus or dissociative recombination, so collides with electrons. Okay. Right. And so that way would make H2. Okay. So here's a plot again that I showed before, the H2 abundance, function of redshift. Right. So less than redshift of 100 or so, the H minus channel is important. Okay. But this rise here in this plateau is due to the H2 plus channel. Okay. However, there's a problem, which is that this process, charge transfer, all the chemical models that I know of, they're all based on a single measurement done at room temperature, and the rate is assumed to be a constant. Okay. There are other measurements and even calculations, but they're all at really high temperatures, not really astrophysically relevant. Right? And so far today, we're still using just the rate coefficient here for this process. Right? So this introduces some uncertainty in our prediction of the H2 abundance through this mechanism. Okay? And then I feel like to suggest that if the H minus channel is suppressed by distortion photons, then this mechanism could be even more important than previously considered. Okay, so let's do a test. So a test could be, oh yeah, so I forgot to mention that this was pointed out also by Cherzoy in a different context, but they mentioned that if H minus mechanism is not important, then maybe the H2 plus mechanism would be relevant. Okay, so I did a test, and that was to just put the H2 plus charge exchange rate coefficient to the Langevin limit, okay, just to see what effect that would be, which is basically almost doubling the current estimate of that rate coefficient. Okay, so the black curve is without the distortion photons, and the blue dots include distortion photons on H minus, and then for the red curve, I increased the charge exchange rate coefficient to the Langevin limit for H2 plus. And we get some increase. Not large, but we get some. And asymptotes out to about 10% increase. Okay. So this rate would have to be a little bit large, much larger than the Langevin limit to be really important, but it has some effect. And you could imagine it could be more important if the rate for the distortion photon attachment was a little bit larger. Okay. So, in summary, I discussed the possible importance of distortion photons in the astrochemical network, as pointed out by Schweitzer and Harada, right, should be considered and considered for all the primordial species, and appears to have an effect on H2, HD, H minus, HD minus, and possibly lithium, and it has no effect on HEH plus. And another thing that's of possible importance is we should look at the H2 plus charge exchange, okay, and the uncertainty in that may affect the predicted H2 abundance. Another issue is just how the rate coefficients are actually used in models. So I thought it would be neat to look back and see how the H2 abundance has evolved over the years. Okay, for various people have calculated it. Okay, and so just looking at redshifts of 10 or 20, whatever they may have given in their papers, here's a plot. Fractional abundance versus the year of the calculation. Okay. All right. And notice also this is a log plot. Okay. So starting back in 84, and sure there are others, and I missed some. Okay. You can see quite a variation, almost a factor of 50. Okay. And these last three all include the distortion photon effect. Before that, distortion photon effects weren't included. And so we're not talking about 0.1%, we're talking about the factors of a few to get the H2 abundance correct. Okay. well, what can we do to make improvements? So in the calculation I showed was preliminary. I just used the Wong spectrum. So we could instead use Cosmo-Rec to get the full distortion spectrum as a function of z, and improve our calculation of the distortion rates. Okay. We could apply it to other species. If you're interested in lithium chemistry, lithium minus is probably also important there, which I didn't have a chance to test. Okay. To really get the rates correct for molecules, one really needs to solve for the state-dependent chemistry and excitations, okay, which is very difficult to do. There's been a few attempts. Flower tried this for HD, and Harada and Padaman tried this for H2+. Okay, the problem both those have is that there are much of the data that's needed is just not known. So they made a lot of estimates, and it depends on what level you want to do it. Flower did just the vibrational resolved, and in this paper they also tried to include rotational resolve, but there's not really much data to do a correct calculation. Okay. And let's see. Oh, so let me acknowledge some of the contributors to the work here. Okay. So a lot of the work was done by my two recent students, Shinya Miyake and Chris Gay, and this is a snapshot of my group 2 years ago. And I acknowledge the collaborators that contribute to some of this work, Stephen Lepp, Brendan McLaughlin, Alex Dargano Hussein, and Robert Foray. And as the last thing I wanted to do is to make an advertisement. If you're going to be here next week for the AAS meeting, we have 4 contributions at the meeting in the laboratory astrophysics session. On Monday, we have a poster on charge exchange and also on photo dissociation. On Wednesday, have a poster on collisional excitation. And Hussein's given a talk on this H- photo detachment work on Wednesday. And with that, I'll stop. Thank you.
Questions?
Okay. Just
Maybe some questions about this solver or state undependent calculation for Cosmo-Rec. So Cosmo-Rec also includes the effect of the radiative transfer and also the distribution of photons. And it turns out that because of the diffusive broadening of the line and alpha line is shifted quite a bit with respect to the norm scattering approximation.
okay.
If you just do the calculation and look at the spectra, the normal delta function approximation without the scattering effect, you can see quite significant shift.
Okay.
Towards the wedge side, so I will put that out.
Okay.
It should be shifting the significantly shifting, I think, these positions where the distortion.
Okay.
Maybe that's why I ordered some money.
Okay. Yeah, that would have some effect because you may have noticed in some of the distortion rates there was a drop off when the photons, get longward of the thresholds. Right. Okay. Okay.
So you mentioned the excitation for things like HD and calculating the rates. Is that likely to be a large effect?
Well, for HD is actually known pretty well. It's more the chemistry is not known, but so at redshift, let's go back and see. Let's see. Where is HD formed? I probably should skip it. Oh, one more. So let's see. So right. So for HD, where it becomes abundant, the density is probably very low and the temperature is not high. So the excitation rates are probably not too important. Not going to get very high excited rotational states, but the chemistry of how HD is made is not well known. It's not resolved vibrationally. We only know one rate for the total. That's this charge exchange rate. Let's see. Like this one. this rate here. Okay. So we don't need to know to what other rotational vibrational states are formed in that reaction, and those aren't well known.
Great.
Right. Thank you.
Thanks everyone for. Oh, I don't need that. Put on YouTube. I'd like to thank everyone who came, especially the diehards who remained until the very end. Putting together a workshop. He left because he had to leave. Putting together a workshop requires some organization, clearly, but ultimately, what guarantees the success of a workshop or a conference are those who attend and participate in all of its activities, including giving talks and discussions, watching the posters and everything else. So for that, I thank everybody. But I'd like to take the liberty on your behalf to thank the main two people who have been in contact with you throughout this workshop, who have put this workshop together. Lisa Bastille from ITAM and Greg White from ITC. And I also like to thank Jim Babb, who also helped out a lot for the organization of this workshop. So I know that some of you are staying behind for this AAS meeting, those who came from outside of Boston. So, I hear that this weekend the weather is supposed to be much better